In section 1.4, I will discuss how to interpret position versus time graphs. In general, there are three aspects of graphs that you may need to interpret. These aspects include slopes, areas, and intercepts. The slope of a graph will show you the rate of change in the y variable with respect to changes in the x variable. Areas can be useful to calculate the cumulative product, or y times x, of the x variable and the y variable, and this will be very important starting next chapter. Intercepts can show you the y value when x is 0 or the x value when y is 0. These can be important points in the motion of an object or for determining important values in a data set. We'll start by discussing the meaning of a position versus time graph. And remember that we use the symbol x to represent the position of the object and t to represent time. You should recall that the equation for the slope of a line is equal to the change in the y-coordinate divided by the change in the x-coordinate. And sometimes we'll refer to this as rise over run. The rise, or the change in the y-coordinate, is the change in the object's position, aka the object's displacement delta x. And I know this can be a little confusing because delta y is actually, in this case, delta x. We use x in this case to represent the position and not the x coordinate. Here the x coordinate is time, not position. The run, which is the change in the x-coordinate, again, I know that's confusing, is the time interval delta t. Substituting the relevant variables into the equation for slope, we see that slope is equal to delta x over delta t. And you should recall that delta x over delta t is the definition of velocity. Therefore, the slope of a position versus time graph is equal to the velocity of the object. And this is super important. You're going to be used to use this to interpret graphs for the rest of this course. Also, it's important that you can conceptually connect the idea of the slope of a graph to the meaning of that slope. Interpreting the meaning of certain aspects of a graph is an extremely important skill. This example asks us to find the velocity of an object whose position time graph that you can see here. You'll use the fact that the velocity is equal to the slope of the position versus time graph. To find the slope of a graph, we first need to choose 2 points on the graph. And when you're selecting points from a graph to use for a calculation, it's best practice to choose 2 points on the graph that pass close to the intersection of marked coordinates, and that reduces the estimation. And you should try to choose points that are far apart from each other to improve precision. So the 2 points that I'm going to choose are shown here. I'm going to choose points 0, 0, and 8, 20. So remembering that the velocity is equal to the slope, and the slope is the change in y over the change in x. The y changes from 0 to 20. And always recall that changes are always final minus initial. So 20 minus 0 for the change in y, and 8 minus 0 for the change in x, or 20 meters over 8 seconds. And when I put that into the calculator, my calculator says it is 2.5, and then the units would be meters per second. Okay, notice that the slope has units, and the units are the same units as we have for velocity. That reinforces the idea that velocity is equal to the slope of this graph. And we can use the fact that the velocity of an object is equivalent to the slope of its position versus time graph to infer even more information about its motion based on the graph shape. For example, if we have a linear graph, linear graphs have constant slope. Therefore, a linear position versus time graph implies constant velocity. Constant slope implies constant velocity. So for this slide, it asks, what can we tell about the motion of objects shown in these position versus time graphs? Remember, the main idea here is that the velocity of the object is equal to the slope of these position versus time graphs. So for A, we should notice that this is a horizontal graph. Horizontal graphs have zero slope. So that's going to imply that the object shown here has zero velocity. So graph A is showing an object that is at rest. Okay, for graph B shows a linear graph. Linear graphs have constant slope, so we can infer that object B is moving with a constant velocity. We can infer that it has a positive velocity because it has a positive slope. And this is a very steep line. A very steep line would imply a very large slope, which would imply a large value to the velocity. So we may describe this as a fast-moving object. And that really depends on the scale of this graph. For object C, again, notice that this is a straight line. Straight lines have constant slope, and therefore we can infer that this object has a constant velocity. We notice that the slope is negative. The graph goes down, and so we have a negative velocity. And if you compare the slope in graph C to the slope in graph B, you notice that graph B has a very steep slope compared to C. So we can, as long as these have the same scale, we can also say that this has a slower speed because it's not as steep of a slope. And for graph D, notice that this one curves. Right? It's not a straight line. And curved graphs have changing slope. The slope over here is rather shallow. The slope over here is rather steep. And if we recall that the slope is equal to the velocity, well, the velocity has to be changing because the slope is changing. So this object has a changing velocity. For objects that move with a changing velocity, we may be interested in describing the object's velocity at a specific instant or moment in time. And this is what we refer to as the object's instantaneous velocity. It's important to distinguish instantaneous velocity from average velocity. Instantaneous velocity describes the rate of change in position at a single point in time, but average velocity describes the motion of an object over an extended time interval. We should also note that for objects that move with constant velocity, average velocity over a given time interval is going to be exactly the same as the instantaneous velocity for any time during that time interval. So there's really no need to distinguish between instantaneous and average velocities for objects that move with a constant velocity. It's only for objects with changing velocity that we require this distinction. Just as with average speed and average velocity, we can describe an object's instantaneous speed as the magnitude of its instantaneous velocity. Instantaneous speed describes how fast an object is moving at a particular moment. Be sure to watch this video from the channel Flipping Physics for a great worked example on interpreting a position versus time graph for an object with changing speed. I'll link this video on Schoology. This slide discusses some of the means by which we can measure an object's speed. One technique involves measuring the distance that an object moves over a known time interval. For example, you could photograph an object while a strobe light flashes at a regular rate. If you knew the rate of the strobe light, then you could determine the time between flashes. Dividing the distance moved from one flash to the next, we can measure the speed of an object. And you're going to be asked to interpret strobe photos or dot graphs later on in this section. Another technique that involves measuring the time that it takes an object to move between 2 points that are a known distance apart. Police will sometimes use this to measure the speed of cars using a technique in a system called VASCAR. An officer will use a stopwatch to time how long it takes a car to travel from one marked location to another marked location that's a known distance away. And then they just divide the known distance by the time, and that gives the car's speed. Speaking of a car's speed, every car manufactured today features a speedometer. A speedometer measures the speed of a car based on the diameter of the car's wheels and the rate at which the wheels spin. Finally, radar can measure an object's speed. Radar works by analyzing a frequency shift of light that gets reflected from a moving object. So if the slope of a position versus time graph is equal to velocity, can we still use this fact to find an object's velocity? If that velocity is changing and if the slope changes? Well, yes, we can still use this fact, but now we have to use the slope at only a single point on the graph. How do we do that? For this, we're going to need what is known as a tangent line. A tangent line is a line that intersects a curve at only a single point and has the steepness of that curve at that point. You'll see this in a few pictures. It's easier to picture than it is to describe. Be sure to watch this video that's shown right here. I'll link to it on Schoology, and this is a great way to visualize what a tangent line is. Here's a graph of an object that has a changing velocity, and there's a tangent line at a specific point t. I could draw some tangent lines at other points. Maybe I can choose this point right here. A tangent line would look something like this. Notice that has a negative slope, where the one that was originally drawn has a positive slope. I could choose a point here that also has a negative sloped tangent line, something like that. And that is steeper than this. You can tell from the steepness of the curve how fast the object is moving. There are some patterns to keep in mind when reading a position versus time graph. The first is the most important, that velocity equals the slope of the graph. All the other patterns that I'm going to mention can be inferred from this fact. As mentioned before, straight lines have constant slope, and therefore a straight line on a position versus time graph indicates motion with a constant velocity. A horizontal line has zero slope, and therefore a horizontal line implies zero velocity, which indicates that an object is at rest. A curved position versus time graph has changing slope, and a changing slope implies changing velocity. So a curved graph will imply an object is changing its velocity. When you see a hill or a valley on a position versus time graph, the top of the hill where the bottom of the valley is going to indicate that an object has reversed its direction of motion, because the slope will have to change from a positive to negative or a negative to positive. And I refer to these points as a turning point. And it's also important to note that the top of the hill or the bottom of a valley, this is true for that too, indicates a position where the object has zero velocity. Prior to this point that you see drawn here, a tangent line would have a positive slope and therefore a positive velocity, and a position after that time, maybe over here, would have a tangent line with a negative slope and therefore a negative velocity. And you have to go through zero to get from the positive numbers to the negative numbers. So at a turning point indicated by the top of a hill or bottom of a valley is going to indicate a position where there is zero velocity. Objects have zero velocity at turning points. In this example, we're asked to interpret a position versus time graph. Part A asks, is there any time when the object is moving in the negative direction? How can you tell? Well, we're looking for spots where the graph has a negative slope. And you can see that the object has a negative slope all the way from points D all the way to point that is unmarked right here at 30 seconds. So at all points from D to that 30-second mark, the object is moving at with a negative velocity because the slope is negative during those times. The only marked point where this is happening is part E, and I can drop a tangent line at point E, and you can see that the gradient there is negative. So point E has a negative slope, and therefore the object is moving with a negative velocity. Part B asks, at what marked point is the object's instantaneous speed the greatest? Well, points A, B, and C all appear to be in a line. The graph is linear between those points, and that's the part where the gradient is the most steep at a marked point. You might be able to say that the graph is significantly steeper, maybe around this point right here, but that's not a marked point. So the steepest marked point is points A, B, and C. So that's where they have the greatest speed. Part C asks, are there any points where the object is at rest? How can you tell? Well, an object is at rest at a turning point and when the graph is flat. So point F, the graph is flat, and so that indicates that the velocity is 0 at point F. And we can also drop a tangent line at point D. Point D is a turning point, and so the velocity is 0 at that point as well.